ones. And why prefer length? Basically, the larger the word length, the better the system performance, and it may be less efficient on occasions when the full word length is not used. Because we only need bits, there could be something to do with performance. So the longer the length, at times some of those bits of the system. So in terms of memory hierarchy, so memory hierarchy is to obtain the highest possible access speed. The idea is actually to improve. You make them hierarchical so that you improve the performance while minimizing the total cost, because you have to balance between performance, which is the speed of processing speed, vis-a-vis the cost of the memory subsystem. So depending on the kind of application that you are running, the kind of memory in terms of the hierarchical structure determines how it is going to perform. At times, it could not require that the kind of application you are running just requires some bit of cache memory, or it requires access to just an external memory. So in terms of hierarchy, we have the auxiliary, which is magnetic or magnetic to the memory. We have the cache memory. They all feed into the CPU. Then we have registers, which stores for temporary storage. We have registers, we have cache memory, and then we have which connects to the main memory. Then we have magnetic tapes, and disks that are connected to the main memory. So depending on the kind of application, you can access a specific kind of memory, especially the cache and the register memories that are easily accessed for content or for information that is frequently accessed. Other forms of memory. So in terms of memory subsystem, we have two types. For the read-only memory, the programs that is loaded into memory and cannot be changed, and retains the data even without power. This is permanent memory. This is basically for programs. Programs running on a CPU are stored in the read-only memory, and even if you power it off, you don't lose the kind of information that you have stored on the read-only memory. But for random access memory, it's also called a read-write memory. It's a memory that can have a program loaded and can be reloaded. And it also loses the data once we a different read-only chips masked random access memory. We call it hardwired. For programmable ROM, which is called ROM, by the user, it's not like the data that you have installed may not change. So this one you can change, especially for the programs that you keep installing and you can uninstall, for instance, Microsoft Office. You change from one program to another. We have erasable PROM. It can be programmed for this one and then erased by MiaLite. So that is for EPROM. Then another form of EPROM that is reprogrammable electronically, which is electronic, erasable, programmable read-only memory. It's another form of EPROM, but it's reprogrammable electrically. So, but this is on the chips. On the chips at the point of manufacture, this is the kind of read-only memory chips that you develop. For the different types of random access memory chips, we have the dynamic RAM and the static RAM. For dynamic RAM, the caps are charged and slowly leak until they are refreshed to their original data locations. And an example is actually the computer RAM, because that is one of the ones that you can use to refresh. It's much like a register. The contents stay valid and does not have to be refreshed. And that's why they're static. Static RAM is faster than dynamic RAM, but it costs more. And an example is the cache. So each RAM chip has 2 power n multiplied by m address. So it has n address inputs and m bidirectional data pins. So depending on the m, you can determine the capacity of. Now the operations could be dynamic RAM, and then we have the cache memory, which will be the static RAM, and then we have the CPU. So the correlation between the main memory data from next to current addresses in the main memory, and then the CPU checks to see whether from cache memory, if it is not, the CPU has fetched but if it is not there, it but if it doesn't find it, then it moves to step 4. Where the CPU has to fetch the next instruction from the main memory, which is much slower as compared to if it stopped at stage 3, step. because of that aspect of checking through the multiple operand, say if the n is equal to 64, you can imagine the number of memory access that it has to get to before it finds its operand. So it makes it much slower. So that is what happens. We have the instruction, opcode, address A, then we have the memory. So it keeps on checking through the memory. So if this memory is 2 powers 64, so this